Welcome to lecture 25 for chemistry 141. And the first slide here is on oxyacids, and these are acids that contain a hydrogen and an oxyanion, and an oxyanion would be something like a nitrate ion, a sulfite ion, or a phosphate ion, as just some examples. Now we name them when we are based on the name of the anion and the ending there. So we've got a couple of different situations. So if we have an oxyanion that ends with 8, so the three examples we have up there, nitrate, sulfate, phosphate, they all end in 8, then we give the acid the base name of the oxyanion plus ic. So nitrate, the base would be NITR, so we say nitric acid. If we have something that ends in ite, so something like the NO2 minus ion, that would be nitrite ion. So if in that case we would say that that is nitrous acid, we take that same base name of the oxyanion, add an OUS, and then use the name acid. So we have nitric acid, nitrous acid. We have sulfuric acid, and we also have sulfurous acid as well. Now when we're dealing with acids and bases together, one of the processes that we really look at is the process of neutralization. And so what happens during neutralization is that hydrogen ions and hydroxide ions react to form water with each other, and so they in essence neutralize each other. And so we call this an acid-base neutralization reaction. When we have these reactions, the net ionic reaction we generally end up with is H plus OH minus goes to H2O. Now we also get a salt produced, and as we see in our picture over there, we see sodium ions and chloride ions, and so we would be making the salt sodium chloride, NaCl. It can be anything depending on what the acid and what the base is. This salt is generally a soluble salt. We very rarely see an acid-base neutralization reaction combined with a precipitation reaction. It is certainly possible, we just don't generally see that in chemistry 141. Let's take a look at some examples of an acid-base neutralization reaction here. And here we see HBr and NaOH is our first example. And really for our acid-base neutralization reactions, we're looking at a double replacement reaction. So we can kind of use our ini and outie rule. So we're going to combine our outies there, H and OH, and we can combine our inis there, Na and Br. And so the H and the OH is going to give us H2O, and then the NaBr, we look at how they're combined. Sodium ions have a +1, bromide ions have a -1, and so those come together as NaBr. And so that would be my reaction there. Now we'll take a look at another example here where the stoichiometry is a little bit different. We've got calcium hydroxide, a base, it's a metal hydroxide, plus HNO3. And so here our inis are OH and H+, and our outies is calcium and nitrate here. And when those combine, so we've got our H and our OH, so that's still going to form water here. But notice now that I've got two hydroxides because of that 2 right there, and I've just got that one H+ there coming from the nitric acid. So to balance that, I need to put a 2 out here. Actually, let me go back. Let me change the color of that one. So I'm going to put a 2 out here in front of the HNO3. And that's going to give me 2 H's and 2 OH's. That's going to give me 2 waters here. And then if we look at what we needed for our chemical formula, calcium is in a 2+ charge. Nitrate just has a 1- charge, so I needed 2 nitrates anyways to combine with the calcium. And so that's going to be plus calcium nitrate, so Ca, and then my nitrate will be NO3, 2, because I need 2 nitrates there to combine with my calcium. Now another place we see acid-base reactions is in a process that is called volumetric analysis. And really what we're doing here is we're using molarity as a conversion factor between moles and volume. And we very frequently use this technique with titrations, which is a very common analytical technique. And when we're doing titrations, we use some sort of indicator to show us when a titration is finished. And when that titration is done, we are at something called an equivalence point, where our moles of base and moles of acid, or moles of H plus and moles of OH minus, are equal to each other, and we call that an equivalence point. And we usually use this type of analysis when the concentration of either the acid or the concentration of the base is known, and we're looking for the concentration of the other one. And we can take a look at a graphic here to see what a volumetric analysis would look like. And so there we see that we have an Erlenmeyer flask. We've got acid down here in the flask, probably of unknown concentration. We've got base up here in the burette. And what we're going to do is we're going to have an indicator in here. It's usually something like phenolphthalein, which has no color when it's in an acidic solution, and it has a slight pink color when it's in a basic solution. And so what I'm doing now in the second group is I'm adding base down into that Erlenmeyer flask. I'm keeping track of the volume, so I know the mark on the burette where it started, and I can figure out where it finished. Now as I add that base, it reacts with the acid and turns it into water. And once all of my acid is gone, the next little bit of base I add is going to make this solution basic, and it's going to turn that solution pink, because now that I'm into a basic situation, that phenolphthalein indicator would say you have no more acid, you have only base, you need to stop. And that's where your titration is done, and then you can measure the volume of the amount of base that you used, as long as you know its concentration. Then if you know the volume and the concentration, you know the moles of OH minus, you know that that would equal the moles of H plus. If you know the moles and the volume of H plus, you can find its concentration. Let's take a look at an example here. So we're going to titrate 30 milliliters of HCl using 0.2 molar sodium hydroxide. So we find that the titration requires 48.32 milliliters of sodium hydroxide. So this is what I measured using the burette as I added it in. Once my solution turned that slight pink, I stopped and I read the burette, and I ended up using 48.32 milliliters of sodium hydroxide. So what is the concentration of the HCl? The first thing I need to do is to write the appropriate reaction between HCl and NaOH. Find the moles that I can. So in this case, I have a volume and a molarity of sodium hydroxide, so that will allow me to find the moles of sodium hydroxide. I can use the stoichiometry of the reaction to find the moles of any other species present. And then I can use the given volume that I started with, once I know the moles, to find the concentration of the substance I don't know the concentration of. Well, let's work that one out. So we know this is a neutralization reaction since we have a base, sodium hydroxide, and an acid. So our net ionic reaction there is going to be H plus OH minus goes to H2O. Now we can only find the moles of sodium hydroxide here because that's the only thing I know the molarity and the volume of. So let's go ahead and do that. So we've got 48.32 milliliters, and the first thing that we've done is converted our milliliters to liters here. So our milliliters is going to cancel, leave us with liters. We're going to multiply our volume by our concentration. That's going to allow our liters to cancel out, leave me with 0.00966 moles of hydroxide. So now I'm going to take that value here and I'm going to move it down here. Say, okay, since I needed that many moles of hydroxide, how many moles of H plus did I need? Well, our stoichiometry tells us it's a 1-to-1 ratio between H plus and OH minus. So my moles of hydroxide cancel here, leaves me with moles of H plus. I take that answer right here and I move it down here. And so now I know my moles of H plus, and there's 1 H plus per every 1 HCl. My moles of H plus cancel, leaves me with 0.000966 moles of HCl. And then I take that value and divide that by the total volume of HCl that I had in there, which was the 30 milliliters, which is 0.0300 liters, and I get 0.322 molar HCl. Let's move on to another type of reaction. We don't do much with this type of reaction, but depending on the field that you're going into, this could be a very important reaction for a qualitative type analysis. Now, and this is a gas evolution reaction. And so one of the identifying tests that geologists do when they're out looking for their rocks, looking at an unknown rock, they might apply a drop of acid to a rock sample to see what happens. And if that sample bubbles, there's a good chance that that rock has some limestone in it, calcium carbonate, CaCO3. So calcium carbonate reacts with acid by this reaction. You have CaCO3 plus 2HCl, and we have kind of an intermediate reaction here where it makes carbonic acid, H2CO3, and CaCl2. So we've really just kind of done a double replacement there. And then the H2CO3 then further decomposes into water and carbon dioxide. So it comes off there and makes those two substances, and then the calcium chloride is left over. But we do see here that we've got this carbon dioxide, and that bubbles out as a gas during a reaction. So it turns out that different acids create a lot of different gas evolving reactions, just depending on the type of compound to which you've added the acid. And here's just a quick little table on that. And so we've got sulfides that just don't seem to go through any intermediate, and they evolve H2S, and there's an example there if we had potassium sulfide. Carbonates evolve carbon dioxide gas, sulfites, bisulfites evolve SO2. The ammonium type cation there makes ammonium hydroxide with the water. It evolves NH3. I've never really seen this as what's considered to be a gas evolution reaction. It's just one way of looking at this type of reaction. So, and even the book mentions that. Now, one of the more important types of reactions we do in solution is called an oxidation reduction reaction. Now, if we go back for this chapter and look at all of the reactions that we've been doing, really all of our reactions have just had our ions exchanging partners, moving from one cation to the other, or one anion to the other. Oxidation reduction reactions, which are also sometimes called redox reactions, have more involved reactions going on, and they have electrons actually changing places from one element to another. And here's an example here. So if we have iron plus copper sulfate going to iron sulfate plus copper, we can break that down into a net ionic reaction, and what we see is that we have our iron going from a metal into a iron 2 plus, and then we go to copper 2 plus going to copper. And so electrons went from the iron to the copper. We saw that iron has lost some electrons here, and the copper has gained some electrons here. Now, in order to track the movement of electrons, we developed a concept that is called oxidation numbers or oxidation states. You'll hear both terms, they mean the exact same thing. So our oxidation numbers, in order to look at this, first thing we have to do is to assign oxidation state or an oxidation number to an atom in a reaction. And when we do this, there's a set of rules that we have to follow. Now, these set of rules do in fact vary from book to book, but all of the rules eventually end up in the same place. The rules that I will cover in here and in my lecture will be slightly different from what they do in the book as far as the order, but they'll both get you in the same place. So let's take a look at these rules here. So the first thing we do, so if we're looking at an individual compound or if we're looking at an entire reaction, we still apply these rules, and we apply them in order. So the first thing you want to look at is, do you have any species that's in an elemental form? And if you do, then it has an oxidation state of 0. So an example of that is if you had something that's just iron, just copper, just hydrogen H2, just oxygen O2. So we would assign it an oxidation state of 0. The oxidation state of oxygen in a compound, not by itself, but in a compound, is usually -2, unless it's part of a peroxide, in which case it's -1. The peroxide cases are pretty rare. If you have hydrogen that is in a compound, we assign it an oxidation state of +1. If you have a group 1A element, so sodium, lithium, potassium, that's in a compound, we're going to assign it an oxidation state of +1. If you have a group 2A element, so something like barium or calcium or something like that, we'll assign it a +2 oxidation state. The oxidation state of a monatomic ion is equal to its charge. A monatomic ion would be something like sodium plus, Fe3 plus, Cr4 plus, whatever. You would give it an oxidation state equal to its charge. You can identify a monatomic ion because it's an element all by itself and it has a charge. Now once you get to this point, the sum of all the oxidation states in a compound or a polyatomic ion have to be equal to the charge on the ion or the molecule. So if an overall polyatomic ion has a charge, then the sum of the oxidation states has to add up to that charge. If you have a molecule with no charge, then the sum of all the oxidation states have to add up to 0. Now occasionally what happens is you run into a situation where you have two atoms without an oxidation state having been assigned to them. If one of those is a halogen and you're at this point, then you can assign that halide a oxidation state of -1, but you don't do it until you get to that step 7. Let's take a look at some examples here, and we'll do these in class. You can work on these using the rules on your own. We've got water, H2O, sodium chloride, NaCl, and sodium dichromate, Na2Cr2O7. So those are examples of just assigning oxidation states to individual compounds. Well, that finishes out lecture 25. It was a lot of different material in there. Hopefully it all made sense, but if you have any questions on any of this material, make sure you contact us. Now here's a situation where we are going to be assigning oxidation states to an entire reaction. So once you do that, there's a couple of questions you want to ask. You want to ask yourself, is this a redox reaction? And if it is, then you apply the rules in order. Or actually, you apply the rules in order and then take a look at the oxidation states. If any element changes oxidation state in going from the reactants to the products, then you in fact have a redox reaction taking place. Now once we've decided that we have an oxidation state taking place and we have all of the oxidation states assigned to all the different elements, we want to know what is being oxidized and what is being reduced. We have an oxidation reduction reaction, and that means that we have two processes, oxidation and reduction, taking place. So we always have these two things happening together. So when something is oxidized, something else must also be reduced, and vice versa. So those two processes have to go together. Well, how do we label which process is oxidation, or what atom or element was oxidized and which one was reduced? Well, we take a look at the oxidation states, and what we see is that when something is oxidized, it loses electrons, and that when something is reduced, it actually gains electrons. Well, how do we remember it? Well, we use the term OILRIG or LEOGER. And so OILRIG means oxidation is loss of electrons, and the reduction is gain of electrons. So oil, oxidation is loss, rig, reduction is gain. Then we have LEOGER, and what that stands for is loss of electrons is oxidation, and the gain of electrons is reduction. They both do the exact same thing. Whichever of those acronyms helps you the most, then that's the one you should use. I always like this title of the slide, Agents of Change. We've referred to our species as what is oxidized and what is reduced. And that's more of a passive role as far as the elements. We talk about what happened to that element, but we can also refer to what they did to something else. So the species that is oxidized, so that lost electrons, but it means it also made something else gain electrons. So it caused something else to be reduced. So the material that was oxidized, we say, is the reducing agent. So in that past reaction, it was Fe. The species that is reduced gained electrons. So that means that it took electrons from something else. It made something else get oxidized. And so we call that species the oxidizing agent. In this case, the Cu2+ in that copper-iron reaction. Well, here's an example that will work out in class. We've got iron plus nitrate plus some acid, 4H+, going to Fe3+, plus NO, plus 2H2O. So you want to go through that. We'll assign oxidation states to everything in there, and we'll identify the oxidizing agent, and we'll identify the reducing agent.